I'd like to introduce today's speaker. We're very excited about today's seminar. Holding a PhD from Columbia University, Bruce Mellado is a full professor at the University of the Witwatersrand, a senior researcher of iTembo Labs, and serves as the director of the Institute for Collider Particle Physics. He is the National Contact Physicist of South Africa at the Atlas Experiment at CERN, and is the co-chair of the Nuclear Particle and Radiation Division of the South African Institute of Physics. He is the recipient of several awards and fellowships, and is also a B1 rated researcher of the NRF. Professor Mellado is an expert on the Higgs Boson and was a leading participant in its discovery that was announced in 2012 and led to the Nobel Prize in Physics being awarded in 2013 to Francois Englert and Peter Higgs. Prof. Mellado has attained and continues to have a number of positions of leadership internationally. He is also a member of the Gauteng Premier's COVID-19 Advisory Committee, where he leads work on predictions. He is the co-president of the Africa-Canada Artificial Intelligence Data Modeling Consortium, and his current project received grant awards by the IEEE and the IDRC, and also includes partnerships with IBM and Amazon. Today, he will be presenting a seminar titled "From the Discovery of the Higgs Boson to Modeling the COVID-19 Pandemic, the Role of AI." So please do join me in welcoming Prof. Mellado. I'd like to hand over to him now. Prof, please feel free to turn on your video rather and unmute. And thank you very much. Please go ahead.
Okay, thanks a lot, Diane, for the introduction. I will dive right into it because we've got limited time. So as Diane already indicated, we're gonna go quickly through the discovery of the Higgs boson and how that set the stage for us to get involved as an institute in the modeling of COVID-19, and in particular, what the role of artificial intelligence is in this case. So I will start saying a few words about matter and the Higgs boson. Why is the Higgs boson so important? And its discovery at the Large Hadron Collider in 2012, which will answer the question, why us? And then once I get that out of the way, we're gonna go through some showcases of the use of artificial intelligence. Prior to that, we have to first visualize. So we'll talk about the dashboard, the baseline model we use to advise government, and then a bunch of projects that we've delivered to government on the basis of artificial intelligence, leading to the use of AI for the rollout of vaccination. I should say that this work is in partnership with the Gauteng Province, the Department of Health, the Office of the Premier, and as such, I serve as a member of the Gauteng Premier COVID-19 Advisory Committee, where we do modeling for the province. So let's start with physics. So matter, let me go to the upper right corner, as we know, is made of atoms. Atoms are made of electrons that circle around nuclei. The nucleus is a composite, so to say, structure that is made of protons and neutrons. And we know already for quite some time now that protons and neutrons that make up the nucleus of the atom are composite particles. They have a structure, and those are called quarks. So we can say that the quarks are embedded into the protons and the neutrons, and the protons and the neutrons are bound together into nuclei, and nuclei with electron makes up atoms, and that will lead to molecules and matter in general. So in terms of our understanding of matter in the universe, the known matter, because most of the matter in the universe is unknown, unfortunately, but the one we know, we touch, smell, and interact with on a daily basis, is contained of quarks and leptons, and each quark and lepton has three families. That when we go from the left to the right, particles become heavier, and all those particles have been discovered and verified experimentally. Now, the Higgs boson plays a fundamental role in the theory in that we know particles have mass, they are massive. And if particles have mass, then there's a fundamental theoretical problem. That's why back in the 60s, the Higgs boson or the Higgs field was postulated to explain the origin of mass to these particles. And we've discovered in 2012, so basically almost 50 years later, it's really been a major endeavor in our field. And it's not just the end, but the beginning of a new era. We now live in a new era where we now know how particles acquire mass, and through basically a spontaneous symmetry breaking mechanisms. The Large Hadron Collider was designed, the first discussions back in the 80s. This is a mega project that started taking data in 2010 and continues to do so. We are undergoing a long shutdown, and there will be new data coming in the 20s. Specifically, we'll resume next year. This is basically a bunch of magnets to keep protons in a circular trajectory at very high energies, very close to the speed of light. And there's a bunch of caverns that contain detectors. And those detectors are the ones that people like us contribute to. South Africa contributes to the ALICE experiment here, that, analyzing heavy ions, and the ATLAS detector, Isolde, and also a contribution to theory. So it's a fairly large contribution. Now we have about over 120, 130 people contributing at any given time in South Africa to SEM. So what we do essentially is accelerate the physicists, accelerate protons close to the speed of light. As we know, protons are composite particles that contain partons. Those partons are going to collide head-on to create, using the formula of a special relativity, E equal mc squared, a particle that is heavy. That particle decays, and it is observed in a detector. The detector that we contribute to, the ATLAS detector, is one of the most complex devices ever put together. It's about 40 meters long here. There's about 100 meters below Earth, 40 meters long and about meters high. And you can think of it as a very complex camera that is taking pictures 40 million times a second. So it's really a massive problem in big data intertwined with artificial intelligence in order to dig out very rare signatures from a lot of backgrounds. So that's why, you know, people in our field are strongly work strongly in the area of data science in order to analyze data. This is a picture. Obviously, it's sort of like a schematic representation of all the sub-detectors that the ATLAS detector has. Protons come from the right and from the left, and they collide at the center, and the debris are the ones that are detected. You know, and here we have taken out the detectors that didn't participate or didn't participate strongly in the detection of this Higgs boson, with the Higgs boson decayed into 4 leptons or 4 muon particles. You have this spectacular, very clear event, and this is clearly, obviously, takes decades and thousands of people to really get to work. This is really an amazing event. So the way the Higgs boson was discovered was basically by taking a lot of data, tremendous amount of data, and selecting only those that were very interesting, in this case, 4 leptons. And what you saw is that as the data was being accumulated, my mouse goes around the axis here, we started observing an excess of events that was inconsistent with the standard model without the Higgs boson. And the only way to be able to describe the data is if you add the Higgs boson to the data. This is with the 4 lepton final state. You can do that also with 2 photons. The Higgs boson also decays in 2 photons, and then what you do, you collect 2 photon data and couple those photons to build the invariant mass. And what you saw is that as we're getting more and more data in this region, we had an excess of events that was incompatible with the background only hypothesis. And that's how the Higgs boson was observed in 2012, leading to the Nobel Prize, as Diane indicated, in 2013. Now, this obviously became a major event. Obviously, we remember all that fondly. It was very intense. Some of us spent many years. There are people that even spent 20 years working on it. This is basically the team of analyzers that in a picture in the New York Times, you can see me there with much less white hair. And a year later, the Nobel Prize was awarded to the theorists that postulated the particle. Anyway, so why us? As I've already indicated, in order to do this, in order to discover a particle like this, we need a tremendous amount of data. This is a big data problem intertwined with artificial intelligence. This is a paper back when I was a postdoctoral fellow, fresh from my PhD, where we introduced to the Large Hadron Collider the use of machine learning in order to distinguish Higgs events from background events. This is a classical problem of classification using neural networks. And then obviously in the beginning, that community was not acquainted with machine learning. Then it was obviously, later it became baseline for the searches of the Higgs boson of the Large Hadron Collider. We saw a strong enhancement in sensitivity and robustness of the extraction of the signal in certain final states. That's basically almost 20 years ago. Today, CERN has become a powerhouse for training specialists in machine learning. And this is one of the reasons why the SSN Consortium has such a big number of students that are doing so well in industry today, is the fact that because we need so much data and artificial intelligence to extract our physics message and make a physics measurement, especially when it comes to discoveries, we basically use a large suite of machine learning techniques and develop an intuition of how these work, how to control it, how to understand it, how to basically turn a machine learning algorithm away from a black box, something that we are able to understand and touch and feel and have an intuition about. And there's obviously a large number of visualization tools that allows us to create that intuition. As a result of that, most of our graduates basically end up in big firms and companies doing machine learning as data scientists. So that brings us to the breakout of the pandemic. That was early 2020, where we were approached to basically contribute to the modeling of COVID-19, given our skills, specifically not just in the use of classical algorithms, but in particular the use of artificial intelligence, because one of the things that artificial intelligence is very good at, in addition to dealing with complex problems, is the fact that you can create models from the data, from experience. That's a major asset and functionality that artificial intelligence brings to the table to modeling. If you have a very complex problem that has a lot of unknowns and a lot of parameters, you better use artificial intelligence to help you navigate through that complexity. And that's why AI is such an important element of what people call the fourth industrial revolution in the era of data. And COVID-19 has proven to be yet a problem that is driven by data as well, as you will see. So we created a consortium, the Southern Africa COVID-19 Consortium, with a very strong contribution from our colleagues from Botswana. After we got an award from the IDRC, we basically are morphing into a bigger structure that includes other countries beyond the Southern Africa, following the grant by the IDRC, which is called the ACADIC Consortium, which is now focused on artificial intelligence solutions to managing crisis and also to give early alert to crisis. Okay, so let's start with first visualization. Before you do any AI, you have to visualize, you have to create an intuition. You cannot just get the data, dump it into a neural network and see what happens. It's certainly, there's a bunch of steps that need to happen before AI can make sense and really help you solve the problem. And that is first visualization. So we created a COVID-19 dashboard with a bunch of dashboards in the Southern Africa context that won a grant award, the first, in fact, of that IEEE committee. We created partnerships in countries, specifically in Botswana, where their dashboard became the official dashboard of their government, and Namibia as well. But we also have dashboards in Mozambique, Eswatini, Zimbabwe, Nigeria, and now we are expanding them into Cameroon, and another one expanding the one in Nigeria. It has a structure, but not only does it have basic visualization, but also some modeling that includes also mobility, alert levels, risk indexes, economic modeling, and our dashboards from our partners elsewhere in Africa. one of the nicest dashboards that are the result of our collaborative effort. We developed a collaborative model very similar to the one developed at CERN, where we basically assisted our partners in other countries develop their tools, but they are the ones that are really maintaining and developing them further. We have this very nice dashboard from Eswatini that is updated on a daily basis. Our dashboard is used by about 10,000 people a day. It's not really friendly for the use in a cell phone. It's really for people that are mostly professionals and policymakers to look at the data in a more, so to say, from the point of view of analytics. It's not just a dashboard to see a number. It's really an analytics dashboard that helps policymakers and professions, and we do get a lot of feedback from them. In fact, when we commit a mistake, momentarily within 30 minutes, you have an email saying, "Oh, there's something wrong in that number. We fix it right away." So it's very clear people are really, and we monitor, of course, the usage. And it provides quite a number of visualizations and all that, which basically feeds into modeling. So in terms of the modeling, I'm not going to spend a lot of time here on this because I really want to focus on the AI part, but we needed to answer the question from the Office of the Premier that later goes into cabinet is, what's going to happen in the next few weeks? How big will the second or third wave be? How many beds do we need? So all those questions need to be answered. And obviously you realize that there's a lot of fanciness that you can actually embed into a model, but what you really want is to give a practical answer quickly. And that is really an important constraining factor when you build models that are able to provide an answer, practical answer with certain uncertainties and confidence intervals. So for that, we develop what we call the dual SIRD. There's the classical SIRD modeling compartmental models that had to be modified because what we see in this pandemic is that most of the people that have contracted the virus and can pass it on to other people are asymptomatic and they don't interact with the healthcare system. They don't get tested. That means you have two interactive systems. It's a physical model where you have two groups of people interacting with each other. And one group only, the one that is symptomatic, is interacting with the healthcare system and is tested. But there is obviously, that is the tip of the iceberg. So those two systems have to evolve. And that is why we modify the classical SIRD into the dual SIRD model. I'm going to skip this because I'm running out of time. You basically provide, based on a semi-empirical approach, predictions based on measurements of the adherence to social distancing and non-pharmaceutical interventions and other parameters. You're basically able to give predictions in a dynamic way. And it's important to note that we don't really give predictions 3 or 4 months down the road. We basically give predictions for the next 3 weeks because the system is highly dynamic. It's very, very difficult to predict numbers in a way that is reflective of reality because the way the pandemic works is not as stochastic as you will see in a minute. There's a lot of randomness, so spuriousness, excuse me, that drives the pandemic. All right, so having developed that mathematical apparatus, now we basically have to go further. And we developed the stringency index of the non-pharmaceutical interventions in South Africa. This was a methodology developed by Oxford that we adapted to South Africa in order to answer a very important question that policymakers want to get answered, is what happens if you open schools or close schools while you keep something else open or you make restrictions on something else. So this clearly forces us to create a mathematical apparatus through indexes that try to describe the severity of the non-pharmaceutical interventions, okay? So this is basically an answer to a practical need to address the question of what if. And that's very important for policymakers. Policymakers are always asking themselves the question, what happens if, or what will happen if? And that's why these indexes are absolutely relevant and are embedded into the dual SIRD model that I just described. Another very important aspect of the modeling before I get to AI is that, policymakers need to have a quantitative understanding of when can we move from one level to the other. And the only way to actually do something like that is to basically get a model and create inequalities or differential equations that tell you when you can actually release. And this is an example. I remember when we were moving from level 3 to level 4, where we told government, look, you can go from level 3 to level 4 because this number is greater than the other. That there is a quantitative statement. So we really have to be, we cannot just have a thumbsuck or tell them that, well, I think, or my gut tells me something. You really have to give a quantitative statement. And we developed on the basis of some assumptions, of course, and approximations and inequality that allowed us to tell them when to go from one level to the other. And so far, it's been successful. So modeling, as you see, this is an example of modeling. This is an example of modeling. So let's focus on the red points. The others are anti-correlated, so it's not a problem. You see this modeling working fairly well. That was back in May, before the advent of our first famous wave. And you saw here the emergence of what we call hotspots. So this is not because the model doesn't work. No, it's because there is now a new element that comes into the pandemic, which is the creation of hotspots. And that's not a stochastic process. It's a spurious process that is highly localized, and that requires a different approach to modeling. So modeling, actually, when the data deviates from it, is really telling you a lot. It's telling you that something else is happening that the modeling has not incorporated initially. That means you need to incorporate new elements to your modeling for it to become more sophisticated. And that's why we introduced, and in this graph here, in June, you clearly saw this very strong deviation from between the data and the modeling that we had developed, meaning that there were hotspots were driving the pandemic. Okay, that's really what happens during the peaks or the resurgences or the waves. Hotspots are driving the pandemic. So for that, we basically developed our first project on AI using unsupervised learning, which is the development of a model for hotspots for Gauteng. What you essentially do, you use a technique in unsupervised learning, sometimes called clusterization, with the minimum amount of assumptions. The only thing you really assume is that you have a Gaussian type of distribution within the cluster. Now, clusters or hotspots are mini pandemics that have their own characteristics, their own epidemiological characteristics. So you cannot really predict what's going to happen there in a particular region. You have to really extract it from the data. And that's really where artificial intelligence turns the problem upside down and said, this is what the data is telling us, and then you can start modeling. IBM developed a visualization tool for us. We did the modeling and they did the visualization, and they created a very fancy map where you can zoom in and zoom out. And this was extremely helpful, and it continues to be a very important tool for policymakers to really understand what's happening in their ward, what's happening in their district, and so on, because you can really go down to the street level and understand how many clusters you've got there. Do you have a cluster of clusters and all that, in addition to the fact that we create a severity index. In addition to providing geolocation of the cluster and how big it is and how fast it grows and how close to the exponential growth that cluster is, we're able to combine all the information of the historical data in that region to give us a risk index that helps policymakers understand which of the clusters are the most dangerous. Because you basically have a few hundred clusters in Gauteng at any given time. You really have to pick those that are the really, really dangerous. So that number is extremely important. And that leads, for instance, to some of the visualizations we showed on TV and other outlets doing our engagements with the public. This was, I think, back a month and a half ago, where we had the pandemic had reached its peak. You had a bunch of clusters that were active. The color code gave you a sense of severity, and you saw it was actually very interesting to see how the pandemic was evolving geospatially in the province, how certain regions became less severe, other regions became more severe, and how really it was like how the dynamics of the pandemic works geospatially. It's a very interesting exercise. I will skip this. This brings to another AI-driven project. The SANDF requested us to provide an understanding of the risk for a new wave. I mean, modeling cannot tell you when a new wave is going to happen. Modeling will tell you how the pandemic is going to evolve, given the fact that a wave is starting. Because the problem is that you have is between waves, you have a system in equilibrium, in unstable equilibrium, that will be broken by super spreader events. And you cannot predict when and where those events will happen. For instance, the second wave was triggered, it appears from our analysis and the analysis of other teams, by events towards the end of the school year, because we saw a spike in the number of people that that were seeking medical attention under the age of 20 years old. It was very clear, there was a very clearly defined peak. So we suspected that it was the super spread events that triggered the second wave. So you have basically a feeble and fragile equilibrium in the interim between waves that can be broken somehow. So in order to really understand when that equilibrium is broken, you need early detection algorithms, not necessarily modeling, but it's an early detection algorithm for which we use both classical analytics and artificial intelligence. So I'm going to skip the details of this. This is based on an epidemiological model. We trained this algorithm on about 100 countries around the world and states of the US, just to understand the mathematics, and then of course apply that mathematics with its own parameters specific to South Africa, and then created a website, an interactive website where you can see, you can go to the map of South Africa. This was back in January, of where the risk was highest. Then you can go into the different districts of Gauteng, then the sub-districts of the different districts of Gauteng, and also you can do that for the Western Cape, where we have plenty of information. The policymakers start understanding where are the districts or regions in their province that have the highest risk of resurgence, and when the risk goes below a certain number. For right now, for instance, the risk of a third wave to date, at least for the past week or so, is being low. So we don't have a high risk of the third wave for the time being, but of course that can change very quickly. And we are very concerned about the Easter celebrations as a trigger for the third wave. Introducing artificial intelligence, we are releasing next week a recurrent neural network based algorithm, which basically takes historical data in a multidimensional space, which includes Google, Facebook Mobility Index, and the stringency indexes of non-pharmaceutical interventions. We're working with IBM to also include social sentiment to that as well. It's a very important element to that multidimensional space. And you basically create a model that is time dependent, that you extrapolate to determine whether your data is consistent with a situation of equilibrium, or it's already experiencing a new wave. And we're releasing these algorithms for each province next week. You can see what happens here in the interim period between the first and the second wave. The algorithm, which is in orange, is doing fairly well in capturing the trends. Does not have to agree perfectly. That's not the role of the algorithm. But then when you saw here at the beginning of December, the second wave took off, being completely inconsistent with the green line, which is the extrapolation of the interim period. You clearly see an early alert algorithm coming into play. The same thing in the Western Cape around the end of November. You have a strong departure of the data from the extrapolation of the algorithm, and the same thing for the Eastern Cape, giving you a clear indication that you can use a multidimensional space to refine the understanding of what is a situation of equilibrium versus a super spread events coming in to mess it up. And I will conclude with the role of AI in the rolling out of the vaccination. I've been put in a committee to oversee the recommendations to government of how the vaccine will be rolled out given its scarcity. So which populations are going to be targeted first and how. And this is a complex problem that you have to decouple into different sub-problems. So I'm not going to, I have too much material and I think I'm running out of time now. Yes, I think I'm running out of time. So I'm going to go to the gist of it. You know, there's a three-phased It's a three-phased approach by government. And we took what we call an integrated approach towards it. And I'm going to just show you the results. So what we did is we took the data from the Gauteng Province Department of Health, ran a DNN, a deep neural network on it, and in trying to separate severe disease from the non-severe disease. And then we were able to develop an algorithm that was able to tell us the probability of the population as a function of age, gender, race, and comorbidities to contract the illness. And I think I will stop here. I'm running out of time. We created an algorithm that we've passed on to government and with a bunch of recommendations. You see here basically a ROC curve. On the X is the fraction of the Gauteng population that is vaccinated. On the Y-axis is the reduction of severe illness. So it's very clear that if the algorithm is performed in a smart way, so in a sequential way, when you go from more severe to less severe following this algorithm, with at least no more than 20% of the population, adult population, you can reduce the severity of illness by about a factor of 5. And this was with the first generation of data. We have now more data where we were able to get more accurate results. So this basically highlights the importance of using AI to solve a complex problem. And so when you go through the age distribution from the most risk to the least risk, the artificial intelligence algorithm is able to really pick the right answer. This is why artificial intelligence algorithms are not really black boxes. You can always verify they're doing the right thing for you. You can see here that the people with the highest risk are people above 60, but not just, and this is the important thing. Then of course the age goes lower, but it's important to really understand not just the age, but for instance, things like which are the conditions that lead to severe illness the most, that are correlated with age. This is where classical analytics have a hard time really given those questions. So you realize that people that are at most risk, meaning people that went to the ICU or high care or died, there were folks age 60 or more who had hypertension or other comorbidities. You can see here that of those that are a higher risk, basically about very large number, 70–80% of them had hypertension. Then as the risk drops and go to the least one, these are basically folks that don't have comorbidities. But obviously we know sort of like roughly that, but you really need to understand where to put the thresholds, and that's where AI comes in. Same thing happens with diabetes, hypertension. Diabetes are the leading sources of mortality and severe disease in South Africa and also elsewhere, that are highly coupled with age. So you can have someone who's young with diabetes that don't necessarily has to have the same outcome, and then you can verify that with the data. And you can see the very strong correlation between comorbidities and age. And you can see that in this graph here, where it's not enough to say somebody with of 60 years old or more has to be vaccinated first. Are those folks that have at least 2 comorbidities? And then you verify that those folks that have the highest risk based on the data, they're not just people of age, but people that had multiple comorbidities. Not just one comorbidity, but multiple comorbidities. So this is how you basically start creating more effective algorithms, for the very simple reason that the number of vaccines and jabs is limited. So you have to be very efficient in the way you distribute that. So based on that, and again, this basically brings us to the tension between a researcher and a policymaker. Policymaker does not want to see a neural network, and he doesn't know, nor does he or she want to have to deal with it. They want binaries, they want distribution, they want tables, right? So what you do is you turn that AI algorithm into a classification that policymakers can apply easily when the vaccines come. And then now, instead of having one group of people of above 18 with comorbidities, we have created 4 different groups depending on the probability of the person to contract severe disease. And for that, we created 1 through 5. And also it's important to look at the fraction of the population over 18 that has that. That is extremely important, because policymakers need to know how many vaccines do we need in order to reduce the severe outcomes first, before we reach the herd immunity or population immunity. So then, of course, you have to correlate the entire picture through AI. So this table, as obviously has AI underlying it, but it's presented, the results are presented in a way where the binary is approximating the AI algorithm, and so on and so forth. And this algorithm basically informs policymakers for phase 2Bs. You know, if I go back to the strategy here, we are currently at phase 1. Phase 2 will start once healthcare workers are vaccinated, which is split into 2. Phase 2A, which administers to essential workers, and then comes the phase 2B, which is the population that is that is prone to severe illness. And then will come phase 3, which is more basically to attain herd immunity. But the role of phase 2, it really is to suppress severe illness to the maximum, so that the third wave has the least amount of impact. And that's where data science is extremely powerful. Right, that brings me to the end. Thank you very much, Leanne.
Thank you very much, Prof. That was an incredible presentation, highly informative, and just so well presented. So thank you, and I'm sure on behalf of our audience. So I'd like to now open the floor to our audience to please ask any questions that you may have, because I know, Prof, you kind of glanced over quite a few things. So I don't know if our audience perhaps has questions related to that, or indeed any comments that you might have. So we've got Pina Maleka, you've got your hand raised. Would you like to go ahead?
Hi, Prof. Bruce, thanks. It's Piani Maleka down in Cape Town. Just a quick one. When do we expect the third wave? Anytime soon?
Okay. Hi, Piani. Good to hear you. Okay, so let me go back to the relevant. So this is going to be given by our early detection algorithms, and which are now AI based. So the problem that with the waves is the fact that you have a system in equilibrium where you have a certain rate of community infections that, because the R0 parameter, the reproductive factor is less than 1, sort of basically die out in their community. So that would be a situation of unstable equilibrium. And that can last, as we have seen in many countries and in South Africa, can last for weeks to a couple of months, 3 months. Depends. Now, the problem is that because it's a situation of unstable equilibrium, and this is a physical system of unstable equilibrium, any external factor or any super spreader or several super spreader events simultaneously can break that equilibrium. So that unstable equilibrium, where you have a community transmission but with a reproductive factor less than 1, so that creates an equilibrium, is broken, and then you have an acceleration where the pandemic takes off. So we've seen that with the first wave and the second wave. Now, we cannot tell exactly when it's going to happen. Also, we know that weather has very little impact, or temperature has very little impact. There are other societal factors that come into play. We've had peaks being stopped in the winter or taking off in the summer. So it really is not weather related. So it's not because we have to wait for the winter. No, it's not like that. So the reason why we're very worried now is that we have now Easter coming in. There will be, obviously, because people see that the numbers are low, people also see that the vaccines are coming and there's already a flux of vaccination coming. People think, well, you know, the whole thing is over. So we are very concerned that the Eastern celebrations, which are family driven, will actually may become that trigger for the third wave. Now, unfortunately, if you look at the international experience and also the fact that according to various estimates, there's been measurements of estimates of how many people are believed to have had and how many people are believed to have not had the virus. South Africa is around 50%. So we still have 50% of the population that has not been infected. And that is, if we assume that the new strain does not produce a significant number of reinfections, which is still an open question. And I know that the NICD is making measurements of the rate of reinfection. As we know, South Africa has a particular strain. So I mean, the answer to your question is, we will know typically within 4 to 6 weeks of the peak. So that we know that the numbers of the active cases, hospitalizations, mortality, excess mortality, all those factors will grow in a correlated fashion. And then we will be able to tell basically 4 to 6 weeks before the third wave happens that it's going to happen. But we cannot tell exactly when it's going to happen. Now, on the other hand, on the flip side, it's very, very likely that it will happen because we have a very large amount of the population that has not had it. So we need to get, and the reality is that we are getting prepared for the third wave. There's no question about it.
Thanks, Prof. It was just actually the follow-up was it's just also the concern with the recent probability of students striking. So you might have another possibility of super spreaders in those kind of events, similar to what happened earlier when we had these parties that started in December. So are we guys part of the model factoring these things that if it goes full scale, so we might have some serious issues in our hands before we can vaccinate a lot of people? Thanks.
Yeah, these events are super spreaders. The numbers will go up, and then we will know within weeks what the impact of this protests will be. Once we know they're up, we'll be able to already establish the normalization of the third wave. And so essentially, once we have the first numbers, we'll be able to tell how big the third wave will be.
Great, thank you, Prof. And thank you for the question, Pina. Okay, great. So I'm just going to refer to the first one that I saw here, which was from Fumelani. I'm just going to paraphrase. So is the data that goes into Gaussian models for hotspots predictions daily cases? So nothing else like population in that specific region?
Right, so that's a very good question. So, okay, the most, so to say, sensitive aspect of the modeling is the geolocation. So it took quite some time to get the geolocation right for many different factors, and I don't want to get into. So you basically need data from government that has been processed and reprocessed in order to ascertain the accuracy of geolocations of positive cases. And then you, for the hotspots themselves, we're talking about positive cases. But the importance really comes from, I mean, the complexity of the calculation really comes from the geolocation aspect of the problem. It's difficult to get an accurate picture of geolocation. You have to make some choices as to which points are suspicious. You have a lot of people that don't give addresses, and they give the address of the test station. There's a lot of complexity there. So you basically have to skim through, do some cleaning of your data based on the kind of geolocation you get. Also, we've had this team of ESRI improving the geolocation provided by national and taking into account some knowledge of the local geolocation algorithms. So once you have that, then you apply the AI to create those clusters. So those clusters are basically based on geolocation data that has been tested and reprocessed of positive cases in the province.
Great, Prof. Thank you. I'm aware there's a few more questions. So, okay, the next one that was typed in comes from Olawale from the UKZN. And he says, Prof mentioned that vaccination should be based on comorbidities. What is his advice for a nation whose manner of vaccination is based on elites? In particular, from government officials to security agencies, then health workers and so on.
Okay, that's a very good question, and I think we need to be open about it. So I didn't have time to go through it, but essentially what we did as a committee is to say that we have two types of vulnerabilities, okay? One is, as already indicated in the WHO framework, are social-driven vulnerabilities. So we've created an index of vulnerabilities driven by social factors that directly impact the probability of a person to contract the virus. For instance, the inability to social distance because the person lives in a highly dense multi-generational dwelling, for instance. So those things are known, and we've created an overarching index coupled with population density to provide to government an understanding of where the vulnerable populations are. And then comes an individual-based vulnerability index, which is where AI came in, which takes into account age, race, gender, and comorbidities. But of course, age and comorbidities have the leading discriminating features in those. So after a lot of discussions, because of the fact that we have to give a recommendation that is practical and easy to place, then we basically concluded and recommended to government to basically use both indexes to ascertain the distribution of the vaccine. That being said, we were very open about the fact that we have serious concerns about social vulnerabilities not being taken into account, and I was one of the proponents that were pushing very hard to create an index that policymakers would see and visualize, and it's actually this week or next week going to be visualized through the IBM tool that I showed for hotspots.
Great, thank you, Prof. The next question is from Vuyile Sitaba, who I believe is at Rhodes University. And he says, thanks for the presentation, Prof. A question, how do COVID unrelated deaths that may have initially been deemed COVID related, how do those affect the AI algorithms, since these might contaminate the data?
Right, that's a very good question. So again, I didn't have a lot of time to discuss it, but let me go back to this one. So we are aware that in South Africa, as in other places like Indonesia and Turkey, there is a gap between the number of reported cases, meaning people that died having been diagnosed with COVID-19 at any point and recorded in the system, in the DATCOV system, and excess mortality, which is very well known to be significantly higher in South Africa compared to the actual number of cases that have been reported due to COVID-19. So that is a problem. There's no question about it. And as a data scientist, you need to basically make certain choices in order to create algorithms that are not the most effective, but the most effective for the quality of the data you have. So this led us, and this is the reason that why this slide is here, because we have an incomplete understanding of the picture of mortality in South Africa, which is very well known and established. Instead of developing a model for mortality, we developed a model for severe illness, for which we have a much better understanding, where we put together people that went through ICU, high care, and died, thus minimizing the impact of the lack of data in regard to mortality. Now, then what you do is you look deeper into the data and say, are there hidden correlations, or are there biases or how strong those biases are because you decided to create a model of severe disease as opposed to mortality. And then we basically looked at all the distributions and the outputs from the DNA, and we didn't see a significant difference between somebody that went through the ICU and checked out from the ICU alive and checked out dead. So that clearly indicates there is an element of randomness in somebody passing on, okay? Now, clearly, in the ideal case, we would like to have data from those that didn't make it to a hospital and died elsewhere. That's very clear, and we're not disputing the fact that that is not needed. Absolutely, we need it. But I think after a lot of scrutiny, we were able to conclude that our algorithm could be more effective if we had that information. But in the absence of that information, we are able to give the most optimal answer given the data we have. So in other words, if we had that additional data set, we would be more effective. The algorithm would be more effective in identifying the people with comorbidities. Now, on the other hand, we know and we suspect, we don't have direct evidence, but it's reasonable to suspect that those folks that died without going to a hospital are more likely to be in areas with social vulnerabilities. And that was another of the arguments I put forward to the committee to say we need a social vulnerability index combined with the individual index that we've developed with limited data sets. Therefore, it was absolutely essential for us to put those two at the same level and say there is social vulnerabilities and there are individual vulnerabilities that we know only a fraction of. But we know that in townships, there are folks that have died without interacting. Therefore, this needs to be taken into account. And when the vaccine is rolled out en masse in large numbers, policymakers have to see on the map that the distribution takes into account those social vulnerabilities. So the problem is very complex. You know, I can tell you this has been a very intense experience. I do believe deal with a lack of information by providing the recommendations to counter that lack of information.
Wonderful. Thank you, Prof. And thank you very much to Vuyile for the question.